Section 3.2, Properties of Determinants. First we'll look at a theorem. This is theorem 3, and we want to let A be a square matrix. The first thing we have, if a multiple of one row of A is added to another row of A to produce a matrix B, then the two determinants are equal to one another. So these, we're looking at our elementary row operations. So when we just simply have multiplying one by a scalar and adding it to another, then it doesn't affect the determinants. They're equal to one another. If two rows of A are interchanged to produce a new matrix B, then that determinant of our new matrix is equal to a negative times the original determinant of A. And then if one row of A is multiplied by K, or by a scalar, to produce our new matrix B, then we take, to find the determinant of B, we multiply K, or the scalar, times the determinant of A. Let's look at an example. Here we want to compute the determinant of this 4 by 4 square matrix. So notice that I have one non-zero entry in the second row. So what I'm going to do is I'm going to basically use my matrix of signs. Remember, I have plus, minus, and so then this one will be plus. So I have a positive 5, then multiplied by the determinant of my matrix that I get when I eliminate that row and that column. So I have 1, 3, 4, 2, 6, 10, 2, 7, 11. And what we're going to do is we're going to use the properties we just found in theorem 3. So I want to apply row operations to get this to be a triangular matrix. Makes the determinant a little bit easier to find. So what I'm going to do is I'm going to multiply the first row by a negative 2 and add it to the second. And so what we end up with then is still our 5. Then I have 1, 3, 4, 0, 0, 2, 2, 7, 11. And remember that when I multiply by a number and add it to another row, it does not change the determinant. So now I'm going to do kind of a similar thing. I'm going to multiply by negative 2 and add it now to the third row. So the determinant again is not changing. So I have 5 times 1, 3, 4, 0, 0, 2, and then 0, 1, 3. But notice that my pivot here is in the wrong row. So what I'm going to do is interchange these rows. But a row interchange will affect the determinant. So what we need to do is multiply by a negative. And so now I've got 1, 3, 4, 0, 1, 3, 0, 0, 2. So we just have to keep track of what we're doing. And now I can simply use the diagonal entries to find the determinant of this 3 by 3. So I still have my negative 5 now, times 1 times 1 times 2. So I end up then with a negative 10 for my determinant. A common use of theorem 3C is to factor out a common multiple of one row of a matrix. And remember that this is factoring out of the determinant. Okay, this is not factoring out of the matrix itself, so we're factoring it out of the determinant. So we see then that this second row is multiplied by my scalar k, so I can pull that out and still take the determinant of the matrix that's left, as long as I am pulling it out front and still multiplying by that scalar. So let's kind of apply that. We want to compute the determinant of this 3 by 3 matrix. So looking at the very first row, we see that all the values are even. So what I can do is I can factor out a 2 out of the first row, and I'll have 1, 2, 3 in that first row. Now I have a 1 as my very first entry, and what I can do then is I can apply row operations to get a triangular matrix. So I'm going to multiply the first one by -5 and add it to the second row, and then I'll multiply by a -7 and add it to the third row. And remember that these operations will not change the value of the determinant. So I still have my 2, 1, 2, 3, and then I have 0, -4, -8, 0, -8, -11. And now notice that we could factor out a -4 out of my second row here. So I've still got my 2, I factor out a -4, and I take the determinant of now 1, 2, 3, 0, 1, 2, 0, -8, -11. And then I can apply row operations, so I'll multiply here by 8 and add it to this third row. So I've still got the 2 times -4, and now my determinant that's left is 1, 2, 3, 0, 1, 2, 0, 0, 5. And so I've got a triangular matrix, so I'll be multiplying by the diagonal entries. Keep in mind I've still got the 2 and the -4, but now I'm also multiplying by 1, 1, and 5. And so we will end up with a determinant of -40. So applying these rules from Theorem 3 will help you to find the determinant a lot faster. So here's an example that I want you to work on. I want you to compute the determinant of this 4x4 matrix using a combination of row reduction and cofactor expansion. So basically using what we've just looked at in all of the previous examples, I want you to find the determinant of this using the least amount of operations possible. Show your work and we'll talk about this in class. Suppose that A has been reduced to U, which is an upper triangular matrix with zeros below the diagonal, by row replacements and row interchanges. Then we have that the determinant of A is equal to -1 to the R, where R is equal to the number of row interchanges that we do, multiplied then by the product of the pivots in U, or the product of our diagonal entries. And that is when A is invertible. It's equal to 0 when A is not invertible. So that leads us here to Theorem 4. A square matrix is invertible if and only if the determinant of A is not equal to 0. Theorem 5. If A is an n by n square matrix, then the determinant of A transpose is equal to the determinant of A. And that should make sense since it's a square matrix, the size doesn't change, and we've looked at the definition and theorem stating that the determinant will be the same if I go across any row or down any column. In A transpose, we simply take the rows of A and they become the columns of A transpose. So let's look at kind of a partial proof. We're going to look at the 2 by 2 case first. If I take the determinant of A, B, C, D, just a 2 by 2 matrix, then that is AD minus BC. And let's look then at the determinant of the transpose of A, B, C, D. So the transpose then would be the determinant of A, C, B, D, which will be equal to still AD minus BC, or C times B. So it is the same. And we've shown in a 2 by 2 that the determinants are equal for the original matrix and the transpose. And now let's look at the 3 by 3 case. I want to look at the determinant of a 3 by 3 matrix. And so we have A times the determinant of E, F, H, I minus B times the determinant of D, F, G, I plus C times the determinant of DEGH and when we work this out, we'll have A times EI minus FH minus B times DI minus GF plus C times DH minus GE. And now let's look at the transpose. If I take the determinant of the transpose, then I have ADG BEH CFI, which is equal to A, and we'll go down the first column, times the determinant of EH FI minus B times DG FI plus C times DG EH, which will become A times EI minus FH minus B times DI minus GF plus C times DH minus GE. So we see then that the two determinants are equal. So what we've just shown then is if we looked back at the theorem we began this section with, Theorem 3, it would still hold true if the word row was replaced with the word column, since we've just shown that the determinant of A is equivalent to the determinant of A transpose. Now let's look at Theorem 6, the multiplicative property. For n by n matrices A and B, the determinant of the two matrices multiplied together is equal to the determinant of A times the determinant of B. In this example, we want to compute the determinant of A to the third if the determinant of A is equal to 5. So the determinant of A to the third, remember that A to the third means that we're taking the determinant of A times itself 3 times. So we have 3 A's multiplied together. And my Theorem 6 says that then that is the determinant of A times the determinant of A times the determinant of A. Well, I know that the determinant of A is equal to 5, so I'm multiplying 5 times itself 3 times, and so I will get 125 for the determinant of A to the third. In this example, for n by n matrices A and B, we want to show that A is singular if the determinant of B is not equal to 0 and the determinant of A times B is equal to 0. So when we say singular, we mean not invertible. We want to show A is not invertible. So if we have the determinant of A, B, by Theorem 6, I know that that's the determinant of A times the determinant of B. And we want to show that A is singular if these two things are true. So I'm saying that this determinant of AB is equal to 0. And then I know that the determinant of B is not 0. Well, remember that then the determinant is just a constant. So if I multiply two constants, I can go back to my rules of algebra. If I multiply two constants and get 0, I know that one of them had to be 0, one or the other. And I was told that the determinant of B was not 0. So then I know that the determinant of A must be 0. But if the determinant is equal to 0, then A is not invertible. So therefore A is singular.